Welcome to the Sensors Cortical Area Types tutorial. Other than vision that was covered in the previous tutorial, we support many other types. Some of the sensors in FIGI include infrared, inverse infrared, proximity, accelerometer, gyroscope, battery gauge, central vision, and peripheral vision. An infrared sensor is a device that emits and/or detects infrared radiation to sense its surroundings. Infrared radiation is a form of light that exists just beyond the visible to the human eye spectrum. In FIGI, an infrared input cortical area helps activate neurons when an infrared sensor is activated. According to how many infrared sensors your robot embodiment has, you can extend the infrared cortical areas across the x-axis. In this example, this robot has 3 infrared sensors, so we extended the infrared cortical area to be 3 blocks wide. Here is the physical representation of that robot. When you wave an object that blocks the infrared signals, you can see the infrared cortical areas deactivate in FIGI. Similarly, inverse infrared cortical areas have the same dimensions, but they serve the opposite purpose of regular infrared sensors. Instead, inverse infrared cortical areas activate neurons when there is a lack of activation in the infrared sensor. You can see in this example that when something covers the infrared sensor, the cortical area is activated. Inverse infrared cortical areas are also extendable according to how many sensors your robot embodiment has. The proximity sensor has default dimensions of 1 by 1 by 10, with each block representing a number on an incremental scale of 0 to 9. The proximity sensor is responsible for encoding distance measurement signals. 0 indicates the object is very close, while 9 indicates that the object is very far away. In this physical robot embodiment, as we move the object farther and closer away, you can see the cortical area activation move back and forth along that cortical area. An accelerometer is responsible for detecting the rate of change for X, Y, and Z movements. The accelerometer cortical area has default dimensions of 3 by 1 by 21. The length of the y-axis acts as a scale from negative 100% to positive 100%. A number on the furthest end of the cortical area indicates the highest rate of acceleration change, while 0 indicates that the speed is constant. Values in the middle correspond to their number accordingly, like positive or negative 10% indicating the lowest rate of change. Each column in the accelerometer acts as X, Y, and Z axis indicators. Together, they work together to encode the accelerometer signals in their respective X, Y, Z coordinate. For the first column, the negative and positive values capture the magnitude of the robot acceleration across left and right movements. Negative 10% and positive 10% indicate slower movements, while 100% and negative 100% indicate a greater rate of change. Likewise, column 2 captures the magnitude of robot acceleration across up and down movements. And column 3 captures the acceleration across forward and backward movements. Similar to accelerometer, the gyroscope cortical area has default dimensions of 3 by 1 by 21. The length of the y-axis acts as a scale from negative 100% to positive 100%. A number on the furthest end of the cortical area indicates the maximum angular rotation, while 0 indicates the robot is level. Values in the middle correspond to their number accordingly, like positive or negative 10% indicating minimal rotation. Each column in the gyroscope acts as roll, pitch, and yaw indicators. In this drone embodiment example, you can see that the negative and positive values in the first column capture the rotation of robot acceleration for clockwise and counterclockwise roll movements. Negative 10% and positive 10% indicate slower movements, while 100% and negative 100% indicate faster movements. For the second column, the negative and positive values capture the rotation of the robot for forward and backward pitch movements. And for the third column, the negative and positive values capture the rotation of the robot for left and right yaw movements. Adding accelerometer and gyroscope cortical areas to your experiment allows you to monitor the acceleration and angular orientation of different movements. The battery gauge represents the available battery level. The default dimensions are 1 by 1 by 10, indicating the power on a scale of 0 to 9. A value of 0 means there is not power, but a value of 9 means there is full power available. The central vision cortical area interprets visual signals from a centralized view. By default, it will be in grayscale with dimensions of 64 by 64 by 1. If you would like your vision to include colors, you can extend the Z dimensions by 3, representing a human eye's red, green, and blue color sensing cones. The peripheral vision sensors interpret visual signals from specific views. Respectively, these include top right, top left, top middle, middle left, middle right, bottom left, bottom right, and bottom middle. Together, the peripheral and central visions encode visual stimuli. In this example of Pong and Figi, you can see the ball moving in the central vision. When the ball enters the respective section of the peripheral vision section, you can see the cortical areas activate.